pursue today's optoelectronic devices. So I have only 35 minutes. So I have only chosen two examples. One is organic light emitting diodes, and the second example is organic solar cells. So going forward, so this is the sort of a motivation, and this is going to be a very tutorial in the beginning, a lot of pictures, thanks to Google. So this is the world's first computer. You can see that it's a gigantic, okay? We need multiple people to operate this computer, and it also occupies the massive area. So to, essentially to store this computer, you need a big room, and it is very slow, and essentially, stores a very small, tiny bits of, data. Look at what happened today. Okay, today's computers are tiny. We can just hold in your palm, and the journey from this gigantic screen to this small screen, which we are currently holding in a palm, is essentially a miniaturization of the devices. Now we can, these smaller devices can really, hold a large informations, and they're very fast, and they connect us all over the world. So this is a major change you can see with the first computer and this today's computer. This is the first cell phone, world's first cell phone. This is Motorola developed some time ago, and Dr. Cooper is delighted here to talk with his colleague across the room. This cell phone weighs approximately, what I read in Google is around 3 kilograms. So I look at what happened in today's computer cell phones. So these cell phones are around 100 to 150 grams, and they are our fastest devices today we have. And certainly a journey from such a gigantic devices to the small, tiny devices, molecular electronics indeed made a major difference. Some of the pixels what we are seeing in the cell phone today is essentially a it's a use of molecular electronics has been demonstrated in these cell phones. Although the primary integrated circuits in these computers are made from the silicon, but the color coding here is indeed made use of a organic light emitting diodes. So going forward, you can keep talking about what is the difference molecular electronics has made today. This is a commercial LG organic light emitting diode televisions. Those who have used CRT, I don't know how many people even know in the audience, they have seen this cathode ray tube, a gigantic television. But today's televisions are small, tiny, and very smart, and they look elegant in the room, and they also consume less power. So indeed, the idea of showing this picture is molecular electronics per se has contributed a lot to the energy sector. Again, this is a building integrated photovoltaics. This is a building in Dresden in Germany. You see that the color in the building is it's essentially a integration of a molecule here and use of molecules for solar cell applications. So it's BIP is a very big market in solar cell industry. And here you can see clearly molecular electronics indeed play a role for the energy harvesting purpose. So similarly, you can see OLED monitors have been, there's a major change the way we see today monitors. And then in a future, things are going to change even much better. Samsung Galaxy Fold, where you can fold the cell phone and you can keep in your pocket. So this is indeed going to be a drastic change the way we perceive the electronic devices. The other major change here in the context of energy is for lighting applications. Organic light emitting diodes are going to make a big difference. The currently technologies used based on the compound semiconductor, conventional semiconductor is very expensive, and we are certainly looking forward how we are going to use organic light emitting diodes for lighting applications, a cost-effective way, how we use a light. But there are several open questions here. This is where I'm going to, throw, sort of in-depth analysis on where is OLED, what is the current status of OLED, and how, we can contribute by doing a more fundamental research rather than looking forward for the application purpose. So going forward, why do you even care about it? Why do you want to work in this area? What are the, this molecular electronics, how it is going to make a difference? Let's go back and trace the history and look at what is currently the status of optoelectronic devices. Silicon has a big game changer. People have all the devices currently in my laptop, which I'm using to present this talk, is based on all silicon. Silicon has been traditionally used. The physics behind silicon is very well understood. And this is a choice of material for several other reasons. It's a non-toxic. The availability of material is across the globe. But what are the difficulties with silicon? Silicon is a indeed indirect bandgap semiconductor. So it's a very poor light harvester. If you use for building solar cells, which are currently used for in the market, you have to make a very thick cell. So essentially, it has a fixed crystal structure, and you cannot tune the bandgap much in case of silicon. And everything, when you convert a raw sand, the one which I showed a beautiful image from the Google, is high temperature processing. You need to process a semiconductor at very high temperature to make use of a devices, to convert into devices. And people have miniaturized silicon, up to the death. They have put large number of transistors by miniaturizing. But now there is no further room for miniaturization. Make this statement, which is essentially talking about, can you miniaturize silicon further? So let's look at a comparatively what molecular electronics offer, what silicon cannot offer. So molecular semiconductors are, essentially you can tune the bandgap. The chemical structure which are shown here, from polyacetylene to polycarbazole, here you can easily tune the bandgap of a semiconductor. So based on a desired application, you want to use this material for any application, specifically wavelength dependence light emission, for harvesting light across the solar spectrum, you can tune the bandgap as the way you would like to do it. So engineering functionality in a molecular semiconductor is rather very easy as compared to silicon. So this is one of the major obstacles in silicon, is a fixed bandgap. So I'm sorry. Okay. So essentially you can come over by simply changing this. This is where this field is very interdisciplinary in nature. There are organic chemists who can really tune the bandgap by synthesizing the materials. And then other major aspect of these materials is solution processability. When I say solution processability, means you can put alkyl chains on these semiconductor and you can make them to dissolve in a very common organic solvents. So eventually, when we can make an ink out of it, and you can print these semiconductors on any surfaces, or flexible surfaces, or any kind of surfaces. So that's one of the major advantage, this one. And everything you can do at room temperature. And the morphology seems to be playing a key role, this one here, in this case, which I will discuss a little bit when I go to the solar cell applications. Going forward, why do you care again about the lighting? Let's look at a collage map of a planet. How does it look in the night? You see that lighting required a massive amount of energy. This 14 terawatt energy challenge is for in the context of everything, but lighting essentially need a major portion of this 14 terawatt is lighting. You see the most of the part of the world is brightened here. Okay, you need the light soon after sunset. So it is, and light has direct connections with education. Light can bring changes in the life. So essentially, lighting takes up a lot of energy. So, and some part of the globe is still under dark. If I talk in the context of India, so there is a large number of population, they do not get a simple light in their house. So lighting indeed is becoming a challenge, and how you are going to make a cost-effective lighting across the globe. This is a big challenge, which is, people who work in this area are looking forward to address some of these key questions. And now you can see that lighting is indeed a part of the energy sector. So going forward, look at the lighting options currently we have it. Thanks to Edison, which is incandescent lamp, we use for almost more than 100 years, where incandescent lamp is essentially works on the idea of if you take Okay, so incandescent lamps works on you take any carbon fiber or any some tungsten wire, and you heat and you generate the electricity. So majority of the light, what energy loss is due to heat. So incandescent lamp is not a preferred option, but however, we used that for very, very long time. To come over issues of incandescent lamp, fluorescent light came into the picture. And if you look at the comparatively how much power required to turn on the fluorescent lamp from incandescent lamp is you need 10 watt, and the lifetime of this fluorescent lamp is 10,000 hours. So when the fluorescent lamp is 10,000 hours. You can just compare incandescent lamp is just, these are the numbers which are quoted here. It depends upon how good the power supply you have it. If you have an uninterrupted power supply, constant power supply, these numbers make sense. Otherwise, incandescent lamp can go in a fraction of a second. So compare with the LED now. LEDs and fluorescent lamp, there's a big difference here as well. The LEDs consume a very less power, and they survive for a very long time. 50,000 hours these are the numbers which is simply got it, from some sort of a commercial magazines. But indeed, it is true that LED survives much, much longer. But the current challenge for a scientist which works in this area is the incandescent lamp is very, very cheap. In India, you can buy this incandescent lamp for 10 rupees. Whereas if you go and purchase LED costs you close to 300 rupees. So the challenge is, can you make it something cost effective, as good as incandescent lamp, and develop a technology for, for based on LED. So this is going to be a big game changer in energy sector, where you use LEDs for lighting, but how to make it a cost effective. So the currently which is LED which are available in the market, they are expensive because they all are made based on their conventional a compound semiconductor, where people use a very high processing techniques with a very high temperature, and essentially that's the reason the cost becomes a major factor. So going forward, let's look at molecular electronics here now. Molecular electronics is essentially low cost of fabrication processes, where, as I mentioned before, you can make ink out of it. They are lightweight and flexible. They are wonderful light absorbing materials. So if you want to make a solar cells, for example, the one which I've shown here, a cell phone charger, you can see that you can coat them on any flexible surface, and you can make a charger out of it, because the light absorption coefficient of this material is very, very high. They are wonderful light harvesters. So you can use these materials and you can, coat on any surface. You can tune physical and chemical properties, which I described in the previous slides, where you can change the band gap and physical properties. And can you use such printing technologies? Eventually, there are reports now, already people are printing solar cells by using these polymer ink. So indeed, if you're looking forward, if I make optoelectronic devices by using such an ink, and then make as efficient, as good devices as are currently available in the market, so this is going to make a big game changer in energy sector. So let's look at LED now. What is the figure of merit? As a researcher, when I go to the lab and look at what I'm supposed to, when I ask to build a better LED as compared to the available in the market, there are some figure of merit here. What I've shown here is color purity is very, very important. Suppose, for example, if you're doing a white light emission out of a LED lamp, we need to really address the question of a color purity, because when you use organic semiconductor for making LEDs, they have this emission spectra is Gaussian distributed, where tails are popping up. It is very, very challenging, which I did a little bit discuss in in my talk. It is very, very challenging to get a very narrow emission from an organic semiconductor. Of course, external quantum efficiency, the energy output which you get from the devices, is very, very critical. Operating voltages, you want the LEDs to operate at as low voltage. You do not want to something turn on at very high voltage. And spin statistics is a little bit technical term. Those who are expert in the field, they know what is the spin statistics, which I will talk a little bit when I go when I advance in my talk. But this is where the spin statistic issue is another major problem in this field. So let's look at the history of OLEDs. It started by using anthracene. Okay, anthracene is a simple organic material. We have it's just a fused aromatic ring of 3 benzene. And you see that this Pope, when he did in 1963, what he did is he just put 2 electrodes and tried to make electroluminescence out of it. And eventually you see that the films are very thick here, 10 to 20 micrometer, and turn-on voltages are 50 to 400 volt. This is a sort of curiosity experiment rather than looking forward. So, but this was a good beginning, I would say. And then later, Then there are diodes were made by using AlQ3 is a organic material. This is organic, inorganic material rather. And then you have a diamine is another material to make a dilayer, and Tang introduced this idea of a bilayer, and they could turn out, they can drastically reduce the voltages here up to 6 to 7 volt as compared to this part. So, and then the friend and Andrew Holmes in Cambridge, they use this polymer now. So it's the journey from a small molecule to the polymer here. They did this work in around 1990 here. This is the first polymer material where they wanted to build electrochemical transistors, but they see a beautiful light coming out of a device when they build based on polyparaphenylene, vinylene, a organic pi-conjugated polymer here, which has shown the structure. You can see the turn-on voltages are still 14 to 15, but using polymer idea as a light-emitting diode is very exciting because you can again print them and you can do many things when you use polymer rather than a small molecule. So going forward, what is this photoluminescence and electroluminescence? Again, these slides are initially, as I promised, I made it very basic, tutorial slides for the sake of the students. Here, you see that this is sort of a Jablonski diagram. You can always look at what happens in absorption and emission. So you just excite the electron in excited state by shining a light. You see a fluorescence. This is so you basically populate your Frank condensate state, and the electron which recombines to the hole, you see the fluorescence. And this is when there is a intersystem crosses, when the light comes from the triplet to from the ground state to the S0, then you see a phosphorescence. So this is a very well known. I will not spend much of time. Many people who are audience will be knowing this one. Whereas electroluminescence is slightly different. Electroluminescence is injection of 2 half spins. What you do here is you use an active layer and you have 2 electrodes here. You start applying voltage. When you apply the voltage, you inject a hole and electron. So when you inject a hole and electron in a device, essentially they recombine in emissions in an active layer, and recombination essentially leads to a emission of a light. But here, now look at what happens here. When I would talk about a spin statistics here, I have 2 random spins I'm injecting in an active layer. So one is hole and another is electron. Those 2 spin half particles, when I inject by applying the voltages, how they recombine and what happens to the spin statistics, which I talk. Let's look at here in electrode. So this is where you start building a diode rather than now simply looking at the photoluminescence. You have this is the simple device where I have indium tin oxide, a transparent electrode where the light emitted in the active layer should come out, and I have cathode here on the top. So when I do that, there are many parameters that one need to take care. One is the energy level diagram here. We have to first look at the work functions of the electrode. For example, in the LED's case, you have to look at the work function of I2O, and then your energy levels, they should not be very high barrier for injection. That has implications in voltages. If you have a low barrier here, you indeed inject the whole, electrons or holes, and then this is where multi-layer device comes in picture, where we reduce the barrier from a work function of an anode to the homo of a active layer. So this is the reason why people use this electron transmitting layer and hole transporting. This is HTL and ETL refer to that, where you use electron transporting layer and HTL. They reduce the barriers and then essentially make a device much more that can be turned on at small voltage. Let's look at the spin statistics now. So this is a major challenge in LED, organic LEDs. Here, what happens? You inject hole and electron, which I talked about in the previous slides. So simply look at the spin statistics here. If you take a 2 spin half particles and simply work out the spin statistics here, you indeed what it leads to a 25% singlet state and 75% triplet state. And as you know that the emission from the triplet state to the ground state is the spin forbidden. So this is the light you completely waste when you make LEDs purely based on the singlet state. So one has to work out how we are going to use these triplet states. Triplet states are also not good when you leave it in the device because they generate a lot of heat, and this is not good for the device. So this is one of the challenge in a community, how we are going to use a triplet state. So going forward, when I make a device by simply using a singlet state, let's see what happens here. External quantum efficiency is another parameter I mentioned in the before. You see that external quantum efficiency, the eta is all dependent upon the internal quantum efficiency of the material. So when I make a singlet by simply LED, by using a singlet emission, I can make only 5% for the fluorescent material and 20% for the phosphorescent material. So this is a very small sort of a light which you can see, and these are not really very high quantum efficiency LEDs. So then comes the picture, how are you going to use those triplets? So this question was asked in community time to time, and to progress how we are going to really use a triplets for light emission. So this is a work by Thompson and Forrest. They in a Princeton and in a UC in the University of Southern California. What they did is they used this hybrid material, sort of inorganic and organic material. They used this platinum-based systems, and then they made a use of spin orbit coupling here. So heavier the element, the Z values are large and large, and then by presence of this heavy atom, they use a triplet. So eventually they use this iridium-based, platinum, osmium, ruthenium-based systems, and they make a use of spin orbit coupling, and then we have a very good, make use of a triplet. So, but this turns out to be a very expensive approach where iridium-based systems we really do not want. The idea of generating, using OLEDs, as I said, the major challenge is cost. So we have to use it something very, very simple and viable technology. If you go for such inorganic or organic semiconductor, especially based on iridium and platinum, they are indeed going to be very, very expensive. So this really made a sort of good progress in science. How are you going to do a use of triplet? But this did not attract for the commercial applications much. Then comes the third generation OLED. Here it is interestingly, it is something called now the current status, thermally activated diode fluorescence. Here, this group, Adachi in Japan, around sometime in 2012, it is a very recent sort of a discovery where he used this metal fleet triplet harvesting organic material. His idea was very simple. You use, so here is again what I'm shown is a Jablonski diagram. The difference between S1 and T1 is quite large for organic material. This is called exchange energy. Exchange energy is large, so you don't really collect triplets. So he's come up with the idea, can I minimize the exchange energy? When I minimize the exchange energy, you do generate 75% triplet, but you can collect them back as a, again, this is called a sort of a up conversion mechanism where you have used a thermally activated diode fluorescence. So this is an exciting concept where, organic chemists have to play with how we are going to minimize the delta EST. This itself is a challenging, area where you have to do a rationally design some materials. And this is where my group is very actively pursuing this area, because we find it very, very challenging to use the concept, something, reduce the exchange energy and make use of a triplet. But we found several problems with the TADF material, because the emission comes from the charge transfer states. Essentially, those emissions, have a very low oscillator strength. As a result, and then it's a Gaussian emission again. The color purity has become a big problem. So this is something which is still not a resolved topic, but this is, people are looking forward. Can TADF make a difference in a organic light emitting diode research? So another problem is blue OLED. Blue has been a long-term problem, and this is the question where people are trying to address, which is true in compound semiconductor. Even gallium nitride was developed for blue LEDs, where even this was even indeed a challenging problem in case of compound semiconductor. In organic also, this is very, very challenging, and blue is essential for a display application. If you want to generate a good white light, you have to have a very stable blue light emitting material. So blue has been challenging. I say one of the major problem in the blue is you need wide bandgap semiconductor around 2.9 to 3.1 eV. Once you start developing this wide bandgap semiconductor, then you need to really play with the electrode work function. Can you really have a mismatch? Can you have a minimum barrier between the electrode, and what kind of electrode you are going to use it? And are these materials are going to be a stable material? So this is the major questions. We started working, one of my PhD student now, he has, been postdoc in UK and now he's come back to India. This is the questions we set it up a couple of years ago. How are we going to make it a blue color out of organic semiconductor? And then we basically, a student of mine, where he started this Fluoranthene based derivatives. So Fluoranthene based derivatives, we choose these hydrocarbons basically to achieve a wide band gap in an organic semiconductor. So idea was very, very simple here. I'm not going to show the synthesis part, but indeed what we did is a systematic substitution on a fluoranthene core here, and then we can see that what makes a difference in emission wavelength, what is the essentially LED you can make it out of these materials. We indeed got a blue emission out of these devices. This is a very busy slide. Forgive me for showing such a a sort of busy slide here. And then essentially you see that where your quantum yield is of this material is very high. So emission is maxima was essentially in a blue region. So we get wide bandgap semiconductor, but you see that organic materials often have this color purity problem. You see most of the tails are popping in a green part of the spectrum. So what we need is a challenge is still, how are you going to make it blue, okay, and which is a very, very narrow emission. When you make film, rather it shifts further, because when you make a conjugated polymer solution to the film spectra, essentially you planarize the conjugation and you often see there is a red shift in the absorption and emission. So we also observed the similar things for these materials, and we can see that the emission is further shifted down. So we could get wide bandgap semiconductor, but the quantum yields were also decent for a good, for looking at some of these materials. But however, when you make it devices, we had not really addressed the questions. We must have published one paper, but that was not the goal of this research, where simply stop by publishing one research paper. So essentially, basically if you look at the turnaround voltages are not bad for organic semiconductor, but our external quantum efficiency suffered dramatically. We did not get what we really wanted to, but apart from seeing a blue emission out of this organic semiconductor. So our emission spectra, our external quantum efficiencies were pretty small. So currently, we are really actively involved. I'm not going to show the current TADF project what we have, but we are trying to address two major problems here. One is, can you make a good TADF material with a very narrow emission? And can you make a blue light emitting diodes? So this is the part which is dealt with LED now. I will slowly move towards the organic solar cells. So just again to motivate you, then I will trace a history of organic solar cells. Organic solar cells, are very well known in the field. There are already solar cells have been commercialized in the market. But if you trace the history, Becquerel did this very curiosity experiment in 1839 in his garage, where he just put a platinum in electrolyte solution and shine the light, and he see a photocurrent coming out of it. Soon after that, then there is a flurry of activities in this field. This is a very, very important field to how to make use of a renewable energy for converting into electrical energy, where what eventually sometime around 1940s in Bell Laboratories, first generation solar cells were based on wafer-based solar cells. Please, the generation is not a good word, but you can categorize the material in a different class here. So that's the reason generation word is being used. But wafer-based solar cells are based silicon based solar cells. These are single crystalline material. As I indicated, when you compare silicon and organic semiconductor in my previous slides, there's an indirect bandgap semiconductor, poor harvester of a light, where you see it's a very thick semiconductor. People use around 100 to 250 micrometer. Module efficiencies are pretty decent here, 15 to 18%. When I say module, I have interfacing, I'm putting several cells together, and essentially silicon was the preferred semiconductor as compared to the other one. Let me see how I'm doing with my time. So, okay, so going forward, second generation solar cells are thin film solar cells. Thin film solar cells are where people pursue thin film solar cells to address some of the questions in a first generation solar cells. You see that their amorphous silicon has been used. Soon after use amorphous silicon, the indirect bandgap semiconductor to convert into direct bandgap semiconductor, and it becomes a much better light harvester compared to single crystal the silicon. And you see that already you use a 100 to 210 micrometer thick And the model efficiencies were very, very good. But amorphous silicon suffers with a major problem, something called a Stabler-Ronsky effect. Again, this is very well known in the field. When I say Stabler-Ronsky effect, those who are inorganic students from inorganic chemistry bound background, you see there's a silicon hydrogen bond. Silicon hydrogen bond, when you keep shining a light on that, you kick out the hydrogen, you break the silicon hydrogen bond, and the lifetime of the solar cells dramatically goes down compared to the first generation. So this is something, a persistent problem in the field, and people did not manage to come a solution, a good solution for Stabler-Ronsky effect. Then they looked at the other compound semiconductor, cadmium telluride, cadmium indium gallium selenide, so other class of materials, but they all turn out to be either toxic or they cannot be deployed at a large scale. Third generation solar cells, everything works on PN junction. I'm not going to spend much of time on this one. Third generation solar cells are again a flurry of activities. This is something I was talking in this week itself in a webinar arranged by Society of Polymers Science. Those who attended that webinar and this also, please excuse me, I'm using some of the slides which I used for that webinar as well. So I'm repeating what I said in the same week. Here, third generation solar cells are based on a different class of material. They are called dye-sensitized solar cells, polymer organic bulk heterojunction solar cells, and multi-junction. And perovskite is recently used a sort of a wonder material which people see in terms of efficiency, where the efficiencies are as good as silicon. And if you look at pictorially here, what I've shown here, silicons are very rigid, okay, very thick, heavy, and a third generation material, it's a third generation materials, you can make it flexible. And this is where molecular electronics again comes into picture. You can make ink out of it, and you can print the solar cell technology, solar cells here, eventually by using this one. So I will mainly not talk about all of them here because of the, in interest of time, I will little bit talk about how you make organic solar cells. So the question is always been, since I've been in this field from last 15 years, you see that there is always question we've been asked, will they ever come to the market? But for any technology to bring it to the market, it is important to understand the fundamentals behind it and make sure that so there are very open questions in this field as well. So the working principle of organic solar is slightly different than the PN junction, which I showed in the for the conventional semiconductor. In organic solar cells, what you do is you find type 2 heterojunction. A type 2 heterojunction is essentially how to look at the energy level diagram. Though the P-type semiconductor and N-type semiconductor, you see the HOMO and LUMO here, you shine the light, you generate a exciton here rather than free hole and electron. So this is the major difference between organic and inorganic, where you generate exciton, it's a tightly bound exciton, has a tendency to fall back to and meet to the hole, but rather if you use this type 2 heterojunction and very high electron affinity material like a fluorine, you can transfer this electron and come over the exciton binding energy and collect hole and electron to the respective electrode. So this is this currently, by mixing these two semiconductors, something called bulk heterojunctions have been built, and people use this concept for making a good solar cells. So this is something, again, with something called bulk heterojunction. The blue part is a fluorine and red part is a polymer. You mix together, you make a thin film out of it, and then you can, ideally when you mix together, you form such kind of a domains, and then you have to really do a processing here, and you have to come up with the nanostructured morphology between donor and acceptor. That's very, very critical for organic solar cells. So essentially, that's why morphology in this field becomes a very, very critical. How do you process and achieve this morphology? So going forward, again, in our group, we started this research program. We work in the area of organic solar cells. Our problems are multifold. We are trying to address some of the very fundamental issues. One of the issues where we got interested recently is how you go beyond thermodynamic limit. This is something called Shockley-Queisser limit. This is a theory paper published around in 1961 by Shockley and Queisser. They calculated energy losses. What happens is typically in a solar cells, you shine the light, you generate hole and electron, but the electrons which are in an excited state, they have this vibration losses. And this is the excess energy above the band gap. We lose in the form of heat. It's called thermalization. And the maximum work you can get it done from a solar cells is from the Fermi level. So this is, pictorially I have shown here a spectral intensity versus wavelength. You see that silicon absorbs this part of the spectrum, And these high energy photons are essentially a loss mechanism. And total available energy after the losses of this part of the spectrum as well as this part of the spectrum is the available is 33%. The question is here, can you go beyond Shockley-Queisser limit? Can you go beyond thermodynamic limit? So we looked at, in the case of conjugated polymeric system, the losses are even sort of manifest in pi conjugated system also. In our conjugated system, we generate excitons, and you see that there is indeed a major loss due to this vibration losses in excited state. So this is something which we establish what is the role of this bridge here. When you have a flexible pi conjugated system, what kind of structure it adopts in the ground state and excited state, and how that leads to a vibration losses in the excited state. So this is the work something we did around a couple of years ago by using a Raman spectroscopy. I will not spend much time on Raman, how we did. This was done in collaborations with Professor Jyotisman Das Gupta in TADF, where we look at, by using a femtosecond stimulated Raman spectra, how this bridge plays an important role. Going forward, what we are currently looking at is quickly, I think, if I'm doing okay with the time. So I think I have slightly running out of time. I will run through now the last part of the lecture. Here, what we do, we look at, again, going back to the solar spectrum. You see the silicon is this part of the spectrum. If we have a organic dye, which has a very high energy photon on this part, and it absorbs a blue part of the spectrum, then can you really go beyond Shockley-Queisser limit? The dye, organic dye, which I'm referring here, is can have a property which can undergo a singlet fission. So this is something which people are currently looking at. Singlet fission is a process where you shine one photon and generate two excitons. So for example, pictorially what I've shown here, conventional silicon solar cells, which gives the 25%, and you have if you coat a dye on top of it, you can go up to 40%. So this is some calculations. It's done by Hannah and Nozick here. You see single junction has efficiency of around 30%. And when you coat singlet fission, you can go beyond Shockley-Queisser limit. You can go up to 40%. So we got excited about it. And then we looked at singlet fission, how to design the material for the singlet fission. So this is the fundamental question for organic chemistry here. I was talking about exchange energy here. So singlet fission is the process where you shine photon, you generate hole and electron, and then it can come back to the slow radiative process. But there is other competitive process in singlet fission where you can generate such two TT pair, and then finally you can generate two triplet excitons. So this process is again spin allowed. You can get 200% quantum yield, but you have to meet several criteria. One of the important criteria is energy criteria. As I talked about exchange energy in the beginning, and solid state packing also plays a very important role. So recently, this is something which we wrote a perspective for ACS energy letter, where we talk about what are the molecular design strategies to meet the energy criteria in singlet fission. So there are many emerging fundamental questions in this field. Rather than have a bigger perspective, what is the coupling between chromophore plays a role, whether there's an inter or intramolecular singlet fission, does the mechanism goes through via direct or it charge transfer mediated pathways. So to address some of these questions, so this is my student Krishna Priya. What she did, she coupled this pentacene ladder with a donor acceptor bridge here. The bridge is essentially, what we did is, one of the questions we ask in this project is how the coupling between two pentacene ladders, affect the pathways for the singlet fission, and how it, does this chromophore undergo singlet fission or not. So the pi bridge is very interestingly, way manipulated here. You see phenyl is a pi bridge where you have a poor electronic coupling because of the torsional rotation. So your spin densities are localized on pentacene here. When you use thiophene and selenophene, it's rather planar here. So we have a delocalized wave functions across the chromophore, and there is no sort of a torsional disorder. So by looking at simple absorption spectra, indeed it does. For example, for phenyl bridge, you see a blue shifted. Thiophene and selenophene, you see a red shifted. So we looked at. I'm not going to very detail about ultrafast measurement, but what we clearly see, the phenyl one undergoes singlet fission, whereas thiophene and selenophene does not undergo singlet fission. We had this question, how are you going to explain these results? So we looked at very, very carefully in other two chromophore, no ACF in other two pentacene dimers. But then there was a, we looked at there was theoretical interpretation for this one. You can see that where, when you have epentecene ladders with the coupled with the phenyl bridge, we clearly see the spin densities are localized on pentacene. When you have a thiophene bridge where your delocalized spin densities, then we do not see a singlet fission. So that's a conclusion based on a theoretical, this is how the spin densities are localized on a pentacene ladder. So this is what I'm now, I think I'm already running out of time. What is my own views on this entire molecular electronics? Polymer solar cells are indeed going to make for big way for indoor lighting because they are good light absorbers material. Roll-to-roll printing is very, very exciting. People are looking forward, how are you going to print solar cells? But there are many, many questions here. So I will not read out about all of them, but this is something which is, there are many fundamental questions need to be addressed before even we look forward and commercialize this technology at large scale. So this is my own personal views in on a solar cells. So this is a field, as I mentioned, it's a very interdisciplinary in nature. We need to really collaborate with many, many people. It is important to have collaborations with physicists, spectroscopists, theoreticians, and what you make in your lab is not, if you independently simply an organic chemist making the material without input from these wonderful people whom I met during my academic journey, has really given a sort of very productive research we could do, and we could seriously progress in the field. And without this collaboration, these things couldn't happen. Of course, these wonderful grad students who are motivated always to understand things. Okay, these are the people who worked on these various projects. Abhishek, Tushita, and Krishnapriya, and the postdoc Putraju. And the funding support comes from my different agencies. So with this, I will stop my lecture. I will be happy to answer the questions.